And we're live. So yeah, quick heads up for everyone who watched the recording. There was a bit of a mishap with the schedule, and because of that, most participants were expecting us to have an input speaker today, which is not the case, and I take full responsibility for that, for not disseminating the schedule and the updates to the schedule properly. That being said, we will go ahead with the updated schedule for today. So we are going to talk about chapter 14 in the book, which comes with video lectures 17 through 19. This is the densest chapter in the book. This was a headache to get through, and I probably spent about 20 hours engaging with the content therein in preparation for our meeting slot today. So I hope that what I'm about to present will make sense. I'm not quite sure it will make sense to me. Maybe it will make sense to you, but I am at least somewhat confident that I managed to rectify some of the stuff that McElreef just glossed over in his presentation. And this time, actually, I have to say that, well, first and foremost, if I were to ever do this study group again, I would split up the contents of this week over multiple weeks because it's so much. I also have to say that for the contents of this week, watching the lecture and reading the chapter was actually a really good exercise, because one clarified things much better than the other, meaning the chapter really helped fill in the gaps that the lecture left. But starting on the chapter without the lectures, I think would have overwhelmed me quite quickly, especially because it was another one of those behemoth 50-page chapters. And God damn it, the third edition, please cut this into two parts. So without further ado, I'm just going to go into multi-level models and make sure that I've got my hotspot charging so we don't get disconnected accidentally. And let's just get into multi-level models. 2 electric boogaloo, and we're going to talk about varying slopes and varying intercepts, covariance, and Gaussian processes. You can already tell this is a lot today. I think in total I've got 33 slides. I'm going to move slow here to try and cover everything at a speed which is also good for the peeps who didn't have a chance to engage with the lecture material up front because of the mishap of the schedule. And by the end of it, we'll just see if we feel like delving into the exercises, which I just finished coding up 2 minutes ahead of time, and then now compiling on a different screen. So without any more introduction, we'll get into multi-level models. And we already talked about multi-level models last time, but we only talked about varying intercepts or varying slopes, but didn't really look at how they might interact with one another. And this is what we are going to get into right at the beginning today. So varying intercepts just means that the mean values differ by cluster, whereas varying slopes just mean that predictor effects differ by cluster. Now, of course, we can combine the two to show varying intercepts and varying slopes per cluster, individual, whatever have you. And it's important to point out that average slopes can be just as misleading as average intercepts if you don't know what you're doing. So average slopes need just as much consideration in terms of how to set your priors, how to interpret your posteriors, as average intercepts did from our last meeting. And because of this, we want to apply partial pooling to estimate varying slopes, just like we did with the varying intercepts. That's the big motivation that we go into with today. And so we need to chat a bit more about slopes and intercepts at the same time, because we want to have models that can account for both at the same time. And
can I say one thing quickly? I think like he starts off too advanced, right? Because like you don't have to have a hierarchy to have this concept. You could have like a model that has 2 parameters, and these 2 covariate, right? So if it's just a classical AX plus B, if A is high, then high values would be high. Then you could counteract that by having B being low, so they would be anti-correlated. And therefore, like even without a hierarchy, you could just have this concept, and then you could like level 2 is you do this with a hierarchy such that it can pool both between slopes and between intercepts.
Completely agree. I just think they are not anti-correlated; they would be negatively correlated, because one being high forces the other to be low.
Yes.
Cool. And here's the big kicker. Slopes and intercepts are usually related in some way. Shock, horror, surprise. I know no one saw that one coming. So we need to have an example to walk through. And the example we're going with here, and I have ripped quite a lot of the lecture material here and then just remodeled it a tiny bit to make it flow a bit more the way I understood it. So we're going to go with the cafe wait time example. Basically, we visit different cafes. We visit them in the morning and in the afternoon, and we want to understand our intercept, which is the wait time in the morning, and then the slope, which is the difference of wait time in the morning to the afternoon. That's all we want to get to right now. Now, once we, excuse me, run just a simple model here, we will find that exactly what Jan just said is true. These are negatively correlated. So if you have a long morning wait time, there will probably be either a shorter or marginally longer wait time in the afternoon. But if you have a short wait time in the morning, you will probably have a bigger change to the afternoon. That's what we're saying here. So if you're constantly busy, there's not going to be much of a change in your wait time. But if you go to a cafe which is not that busy in the morning, it might be much more busy in the afternoon. And this introduces a negative correlation of intercepts and slopes. This negative correlation is not generalized. You might also have examples where there's no correlation or where there is positive correlation between intercepts and slopes. Just for this example, we've got negative correlation. Now, if we want to set a prior for how these are correlated, we need a two-dimensional distribution, in this case, a Gaussian distribution, just because it's a Gaussian distribution is pretty neat to look at intercepts and slopes. We might also want a gamma distribution, but for now, we just look at Gaussian distributions. This two-dimensional Gaussian distribution takes a vector of means, which are our alpha bar and beta bar, so just the intercepts and slope average effects. And then it takes a variance covariance matrix, which is what you see right here. I don't know if you can see my cursor. Quick indication whether you can. Cool, thank you.
We can.
Thank you. So we get variance for the intercept, we get variance for the slopes, and we also get covariance and correlation between these. That is a variance covariance matrix. Now, without explaining this one too much for now, we'll get into this one. I want to talk about model specification. And this is where we see the first bit of matrix notation. And because I thought this was dealt with quite rather too quickly in the lecture, I want to spend some extra time on this. So here's what I understand this to be like. First, we get varying intercepts represented by alpha cafe and I just being the indicator of which cafe we're looking at. Then we get varying slopes, which is just beta cafe. Both of these are linked to a multivariate prior with an average intercept and an average beta, average intercept, average beta underneath, and then a covariance matrix. The covariance matrix or variance covariance matrix S defining how much the average intercept and slopes are related. So right here where it says average intercepts, it should probably say average intercepts and slopes, but I'm sure you can extrapolate here. So that brings us to our covariance matrix, which we have not learned how to build yet. And so the big question arises, what's a covariance matrix? How do we get it? We don't look at the rest of the model for now. This is where we stop because we don't know what a covariance matrix is. And so now we need to talk about a covariance matrix. A covariance matrix is an M by M matrix estimation, where M is just the number of standard deviations that we have, or variances, i.e. parameters, which we want to estimate, which might be correlated. For the example, we just have two parameters which might be correlated, but in higher order models, we might have the linear effect of morning to afternoon, and maybe even a squared effect of.
He's back.
Our robot overlord is back.
You're muted, mate. You're muted.
Fuck! Thank you. I have no idea whether the recording is going to be salvageable. And I also don't know where I cut out for you guys.
We were going through you were talking initially about constructing a covariance matrix, I think.
Coolio. So we were already on this slide.
No.
No. Okay.
Slide before.
Cool. Okay.
Yeah.
Thank you very much. This might happen a few more times. I have experienced that when Zoom is acting up, it keeps acting up for me. So when I drop, don't worry, I should be back right immediately. I have no idea where this comes from. Beats me. It's just the perfect way to round off a very terrible week for me. So I will just probably keep dropping in and out. That being said, let's move along. And the big question we have to answer now is, what even is a covariance matrix and how do we construct it? So before going any further into the model at hand, we need to talk about this covariance matrix because we haven't talked about these so far. And that is why I transition us into the covariance matrix explanation. So a covariance matrix is an m by m matrix, with m just being the number of standard deviations, which correspond to average parameter estimates that we want to get to. So in our example, we just have two parameters, hence our covariance matrix is 2 by 2 in dimensions, but we might have a higher order model where we want to look at a linear effect of wait time between morning and afternoon, and also maybe even a quadratic effect. What do I know? Might be interesting to look at. And then we would suddenly have 3 average parameters, which we'd be interested in, because we would have the beta that goes with the linear coefficient, and we would have the beta which goes with the squared data. And then we'd have a 3 by 3 covariance matrix. In these, we have m squared subtract m, then divide that by 2 correlations, because we only need to look at the upper triangle or the lower triangle, excluding the diagonal in these matrices, because they are mirrored along the diagonal. And of course, the diagonal is all going to be non-informative.
Yeah. So m squared is the whole thing. M is the diagonal, and like and divide by 2 because you only care about like half of the triangle, right?
Exactly. So with this, we get to a total of that parameters which are in that matrix. This is mostly you've seen it here, you can look it up whenever you need to build more complex covariance matrices. Unfortunately, specifying something new also means that we will need some more priors, because now we need priors for our covariance matrix parameters. So this is where we get into, now we set some hyperpriors. And for that, we could take the inverse Wishart prior, for example, which is regarded to be not a sensible distribution. This is a quote from the lecture by McElrath, which I think is wonderful academia talk for. I fully disagree with this and think it is shit. Just he is too polite to say it. And he didn't go into too much depth on why he thinks that is. So I also didn't have the time to look into this, so I can't make any more statements about this.
The Cliff Note version is the inverse Weishart is actually the minimum entropy for this distribution, right? So like philosophically, it is like the correct one to do, and it is the conjugate prior. So if you are not in sampling land, it's the one you have to use, right? Because otherwise you can't solve it. So like it has like all of the philosophical properties that we would like. The problem is that you cannot like this decomposition we're talking about now is so nice, because you can talk about how much, like, what do you think is the variance of these parameters, and what do you think is the correlation between, you can set those two priors differently, which is like a much easier way to think about it. And like there might be tricks for trying to do this in the Weishart one, but it's very hard, right? So the Weishart, it's hard to work with, but it's like I think it is like intellectually superior. But I think because it's so hard to work with, in practice, you set the prior, you can't decouple them in the way you want, and therefore you get a worse model. But I think it's like a failure of the human intellect more than it's a failure of the distribution.
Right. Thank you. That was really, really beneficial. That helped me understand it much better. Thank you. So what McElreath suggests is we do decomposition, meaning we split the covariance matrix into a variance matrix and a correlation matrix. So decomposition is the way to go. Again, a quote from the lecture. So now we're faced with decomposition. So we're going further down the rabbit hole, and feeling quite like Alice, we have to talk about what even is decomposition. Well, decomposition is matrix algebra. And this is where, if this was a more packed auditorium, I would expect a lot of cameras to be switched off and maybe even the participant list to just decrease immediately. Thankfully, even though this is matrix multiplication, which is not intuitive for many people because quite a few people do not get taught this, we have some workarounds, which I'll get to in just a second. But in basic terms, what decomposition is splitting up a covariance matrix into a variance matrix, a correlation matrix, and then just the variance matrix again, which is not the same thing as variance matrix squared times correlation matrix, because that's not how matrix multiplication works. And I am just saying this because I had a brain fart myself while working through this. And I went, well, why do you write it like this and not just variance matrix squared, until I realized, yeah, we're talking about matrices, not single values. So this is how matrix multiplication works. Without explaining this too much, because this is simply just to get some intuition, where we're here showing how variance matrix times correlation matrix gives us a certain output, which is then multiplied with the variance matrix yet again to get to our covariance matrix, which we're truly interested in, which is the decomposition part, where you can see that these products result in what S ends up being. This is simply just for demonstration to gain some intuition, because thankfully the computer can do all of this for us without us needing to unpack pen and paper and do this by hand. This is more of a look behind the scenes, and we can almost immediately forget about it. So that explains to us how do we, from simple parameters which get plugged into our variance matrix and into our correlation matrix, are able to get to a covariance matrix, which we then put into our model specification, which takes us right back to model specification. So now we're climbing back out of the rabbit hole. And so now we know how to build the covariance matrix, and we can talk about some priors. And these priors right here are for our fixed effects. So we set some priors for the average intercept and the average slope, alpha and beta, which get fed into our multivariate normal distribution on line 3. We then also have to set an overall uncertainty, or sigma, or variance. Let's not call it uncertainty because that's something else. So another variance, which is sigma, which targets our normal distribution, which is our outcome distribution. So that is line 1, and we're used to this one. Now, the newly added variances to run this kind of multivariate normal model are sigma alpha and sigma beta, which both get funneled into the variance matrix, which is used for the building of the covariance matrix S. Finally, we then, sorry, I added some highlighting here to show you where all of these fit in. Finally, we add a correlation matrix prior, R, which in this case is drawn from a new distribution, which we haven't met before, which is the LKJ correlation prior, which the higher the value in this, the more central correlations are assumed. So something around 0.5 in terms of correlation, sorry, around 0, with the extremes representing -1 and 1. So the higher the value in LKJ core, the more strongly regularizing our prior.
Yeah. The dumb version is basically, it looks like a beta that just goes from -1 to 1 instead of from 0 to 1, right?
And
so a beta 2 looks like
this,
this, and this one looks like this, and a beta 4 looks like this, and this one with 4 looks, it's kind of like a beta, right?
So what we can now say is that values in our correlation matrices constrain each other. because the correlations themselves always have to add up to 1. Make sense so far? So if you're really strongly correlated to one variable, you can be less so strongly correlated to something else. So how do we set a prior for the correlation matrix? That is LKJ core. So we've arrived at the final line of our model specification. We now need to talk about the correlation matrix prior. What we do here is just use the LKJ correlation prior, the one we've already seen. Now, what's important here is to point out, just for the sake of terminology going forward, an identity matrix is just a matrix with 0 correlations and 1s and all of the diagonals. So if you multiply any matrix with an identity matrix, you get the former matrix back at you. And we want to deviate from the identity matrix with our correlation matrix, unless there's absolutely no correlation, in which case our correlation matrix is an identity matrix. So, like I said, multiplying any matrix with an identity matrix returns just the initial matrix. Now, talking about the LKJ prior, and this is actually where I'm going to just throw up the picture at the same time. If we have an eta value, which is the value that gets fed to the LKJ correlation prior, that is below 1, we then go to we go to basically a uniform distribution between -1 and 1. So our model does not I think this is the wrong way around, isn't it? I think I made a grave error here, because an eta value which is lower 1 should actually elevate extreme correlations, whereas an eta value bigger than 1 should reduce extreme correlations, as you can see from the right-hand side.
It would be like a U. If it was less than 1, it would be more extreme.
Exactly, it turns into a U. So let me
just like the beta distribution.
Yes, let me just tab out of this and quickly fix that. Elevates and reduces. Yes, these were just in the wrong order. I apologize for that. Swap these, start screen sharing, back onto that one, correlation matrix prior, there we go. The important thing here is that this prior places no zero mass in any location. And with that is quite the neat prior for a correlation matrix. So this prior is just assigned to each individual correlation which we want to identify in our correlation matrix. So now we know how to do a correlation matrix prior. And usually we want to set a regularizing prior here, as we always do, because we want to get more robust parameter estimates when it comes to predicting out of sample. Unless we don't want a predictive model, in which case maybe we do want an overfitting model. I don't know. Always comes down to what is the goal of our analysis. So with this,
the only thing I don't like about the LKJ prior is it's impossible to say, no, I think my variables are positively correlated, right? Then you have to pick like an eta of 1 or like less than 1, such that you say it's in the extreme part. There's no way of saying like, no, I want the right side. Like they're definitely correlated, but it's positively. That you can't. And I actually don't know how to do that.
That's what I was going to ask. Is there a way to do this in a more one-tailed fashion? Let's say, you know.
I think you would just use a distribution that is one-tailed.
Yeah, but I'm guessing the reason we're using this one and not just the beta multiplied by 2 minus 1, which would kind of look the same, right? I'm guessing there's a reason this one is, there's some special sauce in this one that you lose if you don't use it.
Yeah.
Special sauce.
I mean, you can just, if you know for certain that you fully assume that they are positive, just do a uniform between 0 and 1.
Oh, yeah. I was overthinking then. I just saw LKJ core and I'm like, ooh, nice shiny new toy.
Yeah, when the old Lego bricks still get the job done.
Exactly.
All right. now that we know how to get to all of the individual blocks in our model specification, we can talk about how to code that model. And with that, again, I added quite a bit of highlight to show you how things morph from specification into model code. And the important thing to point out here, I think, is just this multi-normal part right here in our prior for alpha cafe and beta cafe for different cafe classes. And now suddenly you can see that while we've got our sigma represented, we've got our mean effects of alpha and beta represented, we also have our LKJ correlation prior represented. The sigma alpha and sigma beta from the left-hand side are suspiciously absent from the right-hand specification of the model in R. And that's because the new parameter, sigma cafe, automatically contains two elements. Because it knows that there are two elements in the multi-normal distribution, it automatically assumes that now we have two variations here, or variances, which are sigma alpha and sigma beta. We've just called them sigma cafe. So sigma cafe turns into a vector of length 2 automatically. And we can just assign the same prior to both of these. We could assign different priors here if we index sigma cafe 1 and sigma cafe 2, but for the sake of this exercise, we do not. And that's a nice way of how R and the ULAM specification in particular here takes work away from you, but at the cost of potentially hiding a bit of control, which you might want to exert from direct use.
I'm guessing
but you can get around it.
I'm guessing the more common way of doing it would be just to have like exponential parentheses, like square brackets 1, 2, right? So you put in a list there to show that there are two inputs.
This is something I didn't understand from the, I don't know if it was a lecture or something I saw in the text earlier, but literally everything in this package is to make everything explicit. And this was something where I'm like, oh, he's hiding something. Yeah. I initially thought, and I'm like, and it just wasn't too obvious from seeing it notated, because it's really obvious when you see it on the left here, where everything's fitting in. And then when I see the code, it's like, it's getting so nested, it's actually hard to read.
I think this comes down to McElreath knowing his audience and knowing that it would take much longer to get people up to speed with running these explicitly instead of hiding stuff from you. That he tried to make this more user-friendly, but as a result thereof, for people who really want to get through to the basics or basis of this, makes it a bit harder to read.
Yeah, I get that, yeah.
But yeah, I see his predicament, let's just call it that. Mm-hmm. So moving on, we can look at posteriors. And in this case, I'm simply just interested in what happened to our prior of our correlations and our posterior of our correlations. And because we just have two parameters which are correlated, again, the correlation matrix is mirrored on the diagonal. We can just extract samples for the 1 and 2 location in our row matrix. So row is our correlation matrix, and we're just interested in first row, second column. We could have also looked at second row, first column. So the off diagonals, which are mirrored. So this is just the correlation between alpha and beta. And of course, the correlation with itself is always 1. So that's why the diagonals are meaningless. And as you can see here, when we compare the prior distribution to posterior distribution, there has been quite a bit of shrinkage. But also there is shrinkage in multiple dimensions now, because we have multiple dimensions. And so you may have been expecting that we talk about something new, but alas, it's just good old shrinkage again. And so this is where we get to the multiple dimensions of shrinkage, because now we get shrinkage both in the slope dimension as well as the intercept dimension. Where here you can see that the effects of on slope or intercept in the multivariate model have now been shrunk down towards the population mean. So these open circles are closer to the population mean than are the closed circles. And to extrapolate this a bit more, or to show it a bit better, we can talk about this both in parameter scale as well as an outcome scale. And you can see how the negative correlation in parameter scale turns into, still stays a negative correlation in outcome scale. But now on the outcome scale, our ellipses have just flipped direction. It's still a negative correlation that you can see between these, given the shrinkage. But you can see how on outcome scale, status looks a bit different. What I want to highlight with this is simply just that, again, we have multidimensional shrinkage, which is cool, but also we want to plot stuff in outcome scale if we are to explain our model to someone. Which we've talked about so much theory so far, I feel this may have gotten lost. So what is special about multidimensional shrinkage? We have it, it's cool, it sounds amazing, but what does it actually give us? So now we get to talk about multidimensional shrinkage. This all is a thing to begin with because we have a joint distribution of varying effects. The joint distribution being made up of the distribution of varying slopes as well as varying intercepts. And we want to pool information not only between and across clusters, but also across intercepts and slopes to make use of the most information that we can. And this results in a correlation between effects, so slopes and intercepts. When we mean effects here, we mean slopes and intercepts, and potentially more slopes. This then gives us shrinkage in one dimension, which, because of the correlation between these effects, induces shrinkage in other dimensions. So multidimensional shrinkage lets us understand the underlying correlation between effects and lets us make more robust estimates given both of these. So given shrinkage in both directions, meaning we improve prediction accuracy just like before, but much more informed because we use much more information.
Yeah, and the big, like, if you go back one of the big differences between like a hierarchical model and this multivariate one is if you look at the one that is like circled around, right? It basically has like an average intercept and it has like a very extreme slope. And if it was like if each of these just had like a hierarchical thing around it, then both of them would be pooled towards the global mean. So the intercept would stay where it is because it's basically the mean, and the slope would be pulled back. But because when you're pulling back the slope, you're changing the intercept. So even though the intercept starts at basically the average value, when you pull down the slope, you have to increase the intercept. And therefore the intercept actually moves a little bit away from the mean, and we move the slope very close, like much closer to the mean because of this correlation.
Really good. Jan, if I ever end up having to teach a course on this, I will invite you as a guest speaker, be sure of that. All right, now we get to a point which I still hate. And we need to talk about reparameterization of these very complex models. Because with these complex models, we will inevitably run into divergent transitions, which we talked about last time, which shows us that our model is sampling inefficiently and we want to make this better. And this all comes down to reparameterization, as we know from last time. So how do we now reparameterize a matrix into a linear model? Because we need to get rid of our hyperprior on the matrix. And so the matrix needs to be fit into our linear model. And I will fully say right now that I have not gotten to the bottom of this. I think I've got somewhat of an understanding. I know that it has something to do with the Koleski factor. I also know that ULAM can do this for us in some weird way. And for now, I have decided that that is enough for me. I have not fully gotten to the core of how this happens mathematically. So let's walk through this step by step. And ULAM, fortunately, can do this for us to an extent. However, this also shackles us to the use of ULAM. And it might get difficult to modify models like these outside of the realm of ULAM. And I would just like to highlight again that ULAM can transfer the model code which we've written into any stand code. So we can do stand sampling outside of ULAM, just obtaining the stand code from the ULAM specification. So that might be a way of having ULAM do the reparameterization for us, so the non-centering for more effective sampling when applicable, and then try to do some extra stuff with the raw stand code as a result of it. But that's all advanced thinking about future concepts. So let's just talk about how we do this for now. So what we do for now is we can use the transparse line beginning in ULAM specification to then tell it to compose a non-centered from a sigma value, rho value, and some z value. And we can then set a Cholesky prior onto our rho value, which is a prior for our correlation values and the non-centered version of our matrix. Confused yet? Because I was, when I listened to this and when I read through this, and I'm still confused trying to relay it to you now. So I'm more than happy with spending some time on this slide. I am also more than happy to hold off on this until we get to the exercise material, which is where we were tasked with doing this, and I blatantly stole the solution from McElreath's material. And we might get a better understanding of this when we see full model code instead of just these blocks which I cut out. So the important bit here that I'm trying to get to is that composed non-centered can do the reparameterization for us, but now we need the prior for the Cholesky factor, which will be the prior for the non-centered correlations given the reparameterization. So we need to then, when we've run our full model, try to get our correlation matrices back from our Cholesky factors. And to do that, we can just do the Cholesky2 correlation, so col2 chord function on the lower right-hand side. But we would probably just like to do this at the end of each transition in our model, instead of trying to do this for every potentially rejected transition as well. So we then can use this GQ functionality in ULAM, which tells Stan to only execute stuff at the end of each transition. So we have a bit more effective backwards calculation for correlation matrices.
Like, I am like also on team, not fully understanding this, so, but I'll just like try to add like some thoughts here that are like a little bit mumble jumble. So like philosophically, like half of the problem is that it's all of like when you're drawing your samples, you want everything to be independent, because like you're drawing from some prior somewhere. So you're drawing everything in like independent land in the beginning, and then you're doing your like whatever like thing in the space. And therefore, the more uniform that space is, the more like all the assumptions of H and C are going to work out for you. And like, of course, the correlation matrix is like a full matrix that has like numbers everywhere. So that one is like, and by definition, it's a correlation matrix. So like, so like stuff is correlated. That's bad. So then there's this factorization where you can convert it into this upper triangle matrix. And that basically, to just like, we only like philosophically, like this part of the matrix and this part of the matrix, it's just like a mirror image, right? So there's some way of basically making that, like deleting the lower part of the matrix and then fixing your data just that like the dot product does the same thing as it usually does. Like you can like hack the matrix, or like not hack, like just use linear algebra that we're not smart enough to understand. But like conceptually, this like, so if your data is then like mangled around, just that is actually now an upper triangle matrix. Then because then like the first column of that matrix is like a number and a bunch of zeros. So that column at least is like not at all correlated with everything else. And the second one has like only two numbers, so it's only correlated with the previous one. But I always drew that one, so it doesn't matter it's correlated with like dirty math explanation here. So if you just draw them like sequentially in like the way they're ranked, then they're only conditional on the one you just drew, because you have like the rest, like the lower part of the matrix is all zeros. So if you're sampling in that space, then like all the dimensions are like orthogonal, and therefore it goes well. And like if you ask me any question, the answer is I don't know, because like I don't fully get this, but conceptually this is why we're doing it.
That was a good explanation. I do have follow-up questions, but let's not get into it. Let's not get into it, seriously. I'm perfectly happy to talk about this more, but let's just agree to leave it for now, and maybe we'll just have a follow-up session just talking about reparameterization at some point.
I think that's
Because
a really good idea, because I have questions about each line of code here, especially the last two.
I absolutely think this validates its own separate session, which I would just say, let's just tag that onto the end of this study group schedule, because I'm pretty sure we can just run with this. ULAM does it for us, and everyone who wants to stay on and try to understand what it's doing behind the scenes, let's just relegate that to the end of the study series.
Yeah.
I would like to say one thing. Like earlier, I said, like, how do we make other priors to this thing? And like, you just use another prior. Yeah, but like then like doing this is suddenly like way more impossible. Like that's
a really good point. When we started talking about multi-level models and hyperpriors and that sort of thing, I could start to it was easy to visualize, but this,
So now it would be important to find a Koleski version of other distributions, I guess.
exactly.
Yeah. Which I'm sure they exist. But yeah, let's shelve the discussion for a later point in time. That'll also give us time to prepare for it. So let's move on to the big question. We've talked about covariance. Sam knows what's coming up. We've talked about covariance. So what is covariance good for? And now you see what happens if I have been working on this for a long time and had too much tea. Covariance, what is it good for? Instrumental variables and network analyses. Say that again, y'all. I'm just going to leave this.
Legend.
I was actually this close to tweeting it at McElraith because I thought he would appreciate this level of humor.
And actually, you know, from New Jersey, so awesome.
Oh, I didn't realize that. Hell yeah. Woo. Cool. Okay, getting into it though. We need to talk about instrumental variables. And first, we need to talk about the motivation as to why we want to do this. So, instrumental variables all come down to trying to not remove, but understand the confounding effect of something unmeasured by virtue of a natural experiment or instrument or exposure in our DAG. So basically, with this thought example here, we want to understand the effect of E on W, but there's a confound which we haven't measured, so we can't look at it and its effect, which is U. But we might have some information about Q, which can serve as a natural experiment, instrument, or exposure. And instrument is where the name for instrumental variables comes from. So Q is an instrumental variable if it satisfies the following criteria. First of all, Q has to be, it has to be independent of U. So there cannot be a causal relationship going from U to Q. Fine. We've got that in this DAG. Spoiler alert, all of these criteria work out with this DAG. So furthermore, E so Q and E need to be linked, obviously, because otherwise, how would there be any flow of information here? And then lastly, Q cannot have any other influence on W except through mitigation by E. That's how we get to saying this is an instrumental variable. So the question arises, what do we do here and is it useful? And first of all, we need to just throw up the warning that if an instrumental variable is used incorrectly, it can actually amplify the bias that's introduced by U. So I would have actually liked for this to be its own separate chapter, but it was just a tiny footnote in the book, and I tried to squeeze some information out of it, but I'm not quite sure that I managed to squeeze all of the relevant information. So do hit me with questions, the answer to which will probably be, I don't know, and maybe we can figure it out together. So to think about what's happening here, basically we can take the above right-hand side DAG apart and try to think of this in terms of 4 different models. First of all, we have a wage model. which is just trying to explain the value of our last node there, W, through a normal distribution, which is informed by an average wage intercept, the effect of education, and then the unmeasured effect. Now, we don't know the unmeasured effect. Let's just leave it at that. But we do have our wage model. We also have an educational model. The education is driven by an average education level, then some effect of Q, which we can measure and is our instrumental variable, but then also of U, which again is unmeasured. Now, Q is defined in this case. Q stands for quartile in which you were, or quarter in which you were born. So this is first 3 months, second 3 months, third 3 months, fourth 3 months in a year. And the effect that that might have is parsed into education. So because there's no information leading into Q, this is just a Bernoulli model here, because you've got a chance of being born in the first quarter, second quarter, third quarter, fourth quarter, which is roughly equal. In reality, it isn't. For the sake of this example, it is. Because humans have cyclic births, but not in this world, not in this small sample world. Now, the confound has some value, which in this case just comes from a normal distribution. And now we want to try and understand the effect of U through adding some information through Q. And this sounds fuck off weird. So I am just going to go into the statistic model. On the left-hand side, we have the generative model, which tries to explain how we get to our value of W. On the right-hand side, we now have the statistic model, which tries to explain where the different paths come from. So basically what we do here again is just a big ass statistic model with a certain correlation or covariance matrix. So what we get here is we try to explain wage through some education. So we model these together, WI and EI. And what we use here to get to their values is, again, a multivariate normal distribution with some mu, so average wage and average education, which is driven through what we can measure. So education and our quarter of birth. Now, the way this works is that our covariance matrix S now is our error covariance, which gives us information about the effect of U, because it targets this confounding path between E and W and tries to get to their correlation or covariance through anything that's not contained within our generative models, which within our statistic model. Does that make sense? Because I feel like I sound like a conspiracy theorist.
Yeah. So the intuitive hand wavy explanation would be, if on the left side of this thing, if E and W both had like a plus Q, right? So they were both, and Q is sometimes 0 and sometimes 1. Then they of course would be like larger number when Q is true, and when Q is quarter 4, and a lower number when Q is quarter 1, right? And that would cause these, like, because both W and E now has Q in them, they're correlated with Q, right? But we don't crap. So no, if there's like backtrack, we don't have U, right? That's the problem. We don't have access to U. But you can see in the model to the left that U is a part of these two equations, right? And we then like, because both E and W has like U in their regression, it causes these two outcome variables to be correlated. And the only way we can like get at this value of U is via the correlation, because we don't have access to that variable. Like if we had the variable, we just plug it in there. But like we can get around it by having their correlation leak that information to us,
and thereby increase the power of our analysis, right?
But yeah. not this power, right? Like having infinite amount of data wouldn't help you, right? If being well educated and being what is the other one? It's educated and having a high wage, it's just an artifact of having rich parents. Then it's really hard to see what the effect of education is on wage, right? Because it's confounded by having rich parents. And if you have twice as many poor people and twice as many rich people in your data set, you have the same level of confounded. You just have smaller errors on your confounded estimate. So it's not about power, it's about precision.
Precision. Yeah. Gotcha.
But what you can get to is the correlation between E and W, which is not necessarily explained through the causal pathway between them. And that is where we go with our modeling of this whole situation. So thank you very much, Jan, for giving me the setup for my next slide. We now get into, here's a naive model, which is completely lacking the information that the path E to W is confounded. And the naive model just tells us that if you have a higher education, you have a higher wage. And this is where confounding is a real shit show, because we see this, we fully agree with it, we don't think about it much further, we report the results we've done. And that's why drawing DAGs is, I think, such a useful exercise to try and get to potentially confounding effects and alternative explanations of what's happening in your data, which is then also where we go full circle with the mantra of McElreath of practicing model comparison instead of model selection, to get to try to understand the potential DAGs as much as possible instead of settling on just one. So we've got a naive model, which we know we might be able to do a bit better.
And the thing is, like, the naive model makes more it makes better predictions in the sense that, like, the errors on the outcome variable will be smaller, right? So, like, if you're just in like, okay, so like I have a low standard deviation, so it's probably correct, then you're actually wrong, right? Because you're confounded. And that's why this mantra, it's not as intuitive to me of model selection over model comparison, right? Because, like, if you just naively compare them, like if there's an extra predictor variable that will mess you up, having extra variables always gives you power. Like, even if it's like a confounded estimate, right? So, like, just kitchen sinking them all in will often be the winning model, right? But it's not the best model if you actually want to make predictions about like what would happen if I counterfactually made an intervention so people got more education, right? Then you didn't, like, you're not counterfactually, you're also giving the rich parents, so you get the wrong idea of your policy.
See, I think this is very much about how you measure how good your model is, because if you just, as you said, I'm going to use that from now, just kitchen sink everything in, and you just look at AIC values, for example, yeah, it's mostly all of the time going to win out any model where you just pile everything in. But then model comparison comes down to the finer details of the individual parameter estimates and trying to find a model that has sensible and meaningful parameter estimates. Moving on, instrumentality model. So this is where the new hip thing comes in. And this is where you can see that we just use the multinomial distribution, which we've exactly had up here. So this is just transferring it as into code. Shouldn't pose any big issues, to be honest. What I want to highlight is that the effect of BEW, which is the effect of education on wage, has now morphed to be basically zero. So education doesn't have an effect on your wage, but the quarter in which you're born does, which is quite interesting to me because it indicates that if you are born later in the year, you end up having a higher wage. And the explanation that McElreath provides for this is, if you're born later in the year, when you enter school, you will be older than your compatriots. So you will have more time leading up to school. And then this will just go further into later years in life of having had more time to consume more education, thus leading to higher wages.
Eric, I just noticed something. Sorry if I interrupt. So
please go for it.
The instrumentality model reads M14.5, right?
M14.5. Yes.
But in the book, yeah. So in the book, that's M14.6.
Yes, that's because I have pulled these from the slides, which he was showing, and not from the book. You will also see this when we get to the later example of brain sizes of chimps. The model we're using for that one, I'll talk about it when we get to it. But yes, okay. because I've very well spotted, because I'm using these from the slides that he's showing in the YouTube lectures, because that's where he does all of the highlighting stuff. And I just
Mhm.
like to use his highlighting. I end up with slightly different models and different model numbers than what's in the book with the newer version of the book. Well spotted. But yes, here you can see how the effects have changed, but also you can see the effect of the confound identified in our correlation matrix of rho, which gives us the correlation between education values and wage values, which in this case is positive. So this is how you can get back to maybe there is an effect between education and wage, but it might not be causal between education and wage, but confounded by something else.
Yeah, this is made up data, right? Because most likely there would be
Yes.
some effect.
Yes, this is made up data. Unfortunately, even though this sounds cool and whatnot, I mean, it also just gives you so many more candidate models to run. This comes with a problem, or a few limitations, because finding a good instrument is hard as fuck. Excuse the lingo.
Unless you're a geneticist.
Unless you've got simulations, yeah.
No, if you're a geneticist, right? It's very, like, you have 40,000 mutations in like most people. So just find all the SNPs that are like correlated with some outcomes, and then you can actually do, like, you can say, oh, well, I have these 20 instrument variables. I'll just use those to correct for confounding
Right.
of like rich people or like all the environmental things. It's pretty awesome.
It is, but depending on which scale you try to apply your model to, the number of potential instruments just skyrockets. And that's what's making finding a good instrument very difficult. If you have a DAG drawn up, you can use a function in the Dyadic package to let this show you potentially instrumental variables, but this only shows you potential ones. You still have to test whether they're any good. However, we cannot test if an instrument is good. So this all comes down to model comparison and seeing if the results make sense, because weak instruments may just end up being useless. And given different DAG specifications, you might end up with something that looks like an instrument, but just because you haven't considered the full DAG is actually a confound, and then using it is a bad idea. So I think what I can leave us with on instrumental variables and talking about them is simply just saying they're difficult. And if one wants to run an analysis with an instrumental variable, it's probably a good idea to float potential DAGs past other researchers to try and understand if the underlying DAG makes sense the way it is, or whether one might accidentally be including a confound into the model. Because this is highly subjective stuff. And there's no good tests for it. At least no good statistical tests. So now we've talked about instrumental variables. Let's talk about networks. And this is what I'm quite happy that now it comes up. But also, I don't want this to devolve into just networks. Yay! So I'm going to try and keep this brief because we've got a lot more stuff coming up. So networks just basically consists of nodes, individuals in this case, and edges in this case, an exchange of gifts. And individuals in this case not really being individuals, but households. Now, what we want to get to is to try and understand the back and forth effect in this particular network. How much does one household receive gifts from another, and how does the one that receives the gifts return gifts to the other household? So these are so-called dyadic effects because they go in both directions, no outside stuff. Now, to get to that, we could just plot gifts from one household to the other versus gifts from the other household back to the previous one, as seen on the right-hand side. There's a weak positive correlation. We might conclude that, well, there's a positive correlation, so reciprocity is a thing in humans, we're done. And if we want to make a qualitative statement, this might suffice. But if we want to make a quantitative statement or a good qualitative statement, we would like to make this more nuanced. And in this case, we want to look at how much do they give on average, how much do they receive on average, and then how much is explained beyond that through a certain Dyadic offset between the two partners which we are interested in for each connection. Make sense? So what we need to do network-wise modeling is we try to run a Poisson model to understand the number of gifts going from household A to household B. We could also do a household B to a household A. In this case, it's just switching around positions of A and B. No big issue. So to get to that, we need to have our rates, and our rate is a product of an average giving intercept as well as a giving intercept just for A, a receiving intercept just for B, and then the dyadic effect, which is what we're actually after in the end. Now, how do we get to the dyadic effect? First of all, we have two multivariate normal priors here now. One of them just targeting the potentially correlated offsets of receiving and giving gifts. So if you're a household which receives a lot of gifts, you might also be a household that gives a lot of gifts, or it might be the other way around, and these might be correlated negatively or positively, or not at all. We need to figure that out via our prior. Then we also have a dyadic offset, which is the effect of A to B and B to A, which there's a strong hypothesis here that these might just be correlated, strongly positive. Everyone with me so far? Okay, I see nodding and I see frantic writing by Serena. All of these slides are available to you, by the way. So you do not need to feel like you need to take notes unless it's just you're writing down what I'm saying.
Right. It's just, you know, to stay engaged and.
All good, all good. No. I appreciate it. I just wanted to highlight that. And here's how to do this in R. Difficult to understand. I pulled this from the book, by the way, because it wasn't in the slides, but I still wanted to have it up here for sake of completeness. And so the important things to highlight here, I think, are we're trying to model the giving rate of A to B and B to A at the same time, as you can see here. So we have one linear model for the rate of giving from A to B and also the rate of giving from B to A. So we have two linear models in here now. The first column in our GR matrix, which we are doing down here, is the giving offset, whereas the second one is the receiving offset. So this is where we go back to GA and RB in this case. I hope that still makes sense. And we then down here in the dyad effect are composing a non-centered thingy, which is where we apply the same variance for both households in the dyadic effects, and then have our correlation matrix back translated down here from the Koleski factors of our priors in the non-centered version. Shit ton of stuff, which I recommend we either go into at a later point in time or everyone on their own time, because I'd love to get through all of the slides I've got prepared for today.
Yeah, there's
Jan,
something
you
very
unmuted
basic.
yourself.
There's something very basic that I don't understand here. So there's obviously more than two families, right? But you only have gifts A, B, and BA. What is like? I'm confused about something.
I think this comes down to how, yes, this comes down to how the data is structured. So the data has a value HID-A, which is household index A, and household index B.
So it's like a long column thing. It's not a matrix.
Yes.
Yeah, okay.
You could refer to this as, instead of A and B, you could refer this as from to.
Yeah, it's all of the pairs. It's not like the matrix of stuff. Yeah.
Yes. So the columns A and B could hold the values A, B, B, A, A, C, C, A, and so on. Now, when we look at the generalized gifting and receiving, which is what we've just ran with our correlation, we can actually have a look at just the relation between giving and receiving. So this is just our, if we flip back here, this is just this right here. So we're looking at the correlation between giving and receiving on average. And what we find is a negative correlation, which McElreath interprets to mean that the rich give more than the poor. So the richer you are, the more gifts you give out and the less you receive, because the others just don't have as much, so they don't feel like they need to give you presents, or they realize your wealth and you realize your own wealth, so you don't ask people for presents. I think that's without going into the sociology of this too much, quite idealistic explanation of the world. And it might work in this setting, but with end stage capitalism, which we live in our societies, I am quite apprehensive about this interpretation, because I don't think the data in our societies would show the same pattern. But that's just me being negative.
There's also a little bit of shark penguins going on here, right? Where like you have like the correlation between like generalized giving, and then you have the dyad effect, right? So if a rich person gives me a lot of money, and I then give a lot of money to the dyad, then I am like negatively correlated with like in generalized giving, because I gave it all to like my close family in my dyad, right? So that could also be what's going on.
And that's where we get into the dyadic effects. So for this, we look at the correlation matrix of the dyadic effects, rho D, in our code earlier. And what we can see now is that there's a high correlation here, which is a lot of reciprocity, right? Especially if we plot this back again on outcome scale, or outcome scale of household B in the dyad, household A in the dyad. How are the giving rates correlated with one another? And the
dyad is like, it's like these 5 houses are like besties friends, so they give it to each other, right? That's a dyad, right?
No, dyad is just 2 actors. Dyad is just how do we give back and forth between just 2 households.
Okay.
And we try to understand how much reciprocity is there. And the reason we see this high reciprocity rates, the high correlation between giving rate from A to B and giving rate from B to A, that's what this correlation is telling us, is because zero gifting is perfectly reciprocal. So if you do not interact with another household, you give them 0, you get 0 from them. That is perfect reciprocity. It's exactly as much reciprocity if they give you 100 and you give them 100. Make sense?
Yes, but it also looks very correlated outside of 0, right?
Yes, it does. There's a lot of true reciprocity going on here, but our data might be biased towards reciprocity because 0 is included in the data set.
But okay, so the way I should interpret this is some rich guy gives money to 10 people, and then basically these people, they shuffle money around and are like all poor. So there's a lot of correlation between like everybody who gives money, with the exception of the one rich guy, right?
Yes.
So that's why the generalized giving is messed up by really, really poor or really, really rich people. But the dyadic thingy is like is spot on, because it's only like it's only these rich or poor people who are.
Exactly correct. So you can think of this a bit, so that the way I try to think about getting to networks, especially in a Bayesian framework, because it just lends itself quite well to it, is think of yourself trying to chisel a statue out of marble. And if you're less optimistic about what you're doing, you might think you're working with granite instead of marble, because it's not that fancy. And what you're trying to do is chisel away all of the stuff that you're not interested in, which in this case is generalized giving and generalized receiving, so that you are left with just the skeleton of the effects between each other, which would end up being your statue. So trying to remove negative space, basically.
Yeah, and like so the thing is, so like because there's like this model which has 2 multivariate normals, and then there's the original one which had 0 or 1 multivariate normal. I can't remember.
I think I have 1.
Okay. Yes. Yeah. Okay. Yeah. So that okay. Then I totally buy your. I just wanted to. Yeah. I am totally.
Cool. I see a few apprehensive faces. Serena, you look like you're unhappy with what we're discussing, or is it something else that you're unhappy with? Okay. Cool. Not going to go into it. Sam, Ruzan, are you still with us? I don't want to go too fast just to get through it. I'm
with you so far. I'm trying to keep a dag in my head as I'm doing this. So
Cool. Ruzen, you okay?
Yeah, I'm okay. But yeah, I'm a little bit confused with many things. I may need to look at some of the prerequisite for this chapter,
Right.
so to get a better understanding.
If you've got questions, just blurt them out, right?
Sure, sure.
Cool. All right. This is when we get into the next big thing. And I actually think that now we are coming to the last third of my slides on the contents of the chapter, and the last in the 3 of the lectures that we're going with this. And I'll try to keep it slow, even though I just want to get done with this. So stick with me as we delve into continuous categories and covariances thereof. So far, we've talked about discrete and unordered categories. So leave behind instrumental variables, leave behind networks. So far, we've just looked at, here's a bunch of cafes, but we didn't say whether they were ordered because we can't. Now, all of these categories were assumed to be equally different from all others in the prior, which doesn't mean they're all the same away from the average intercept, but just basically they all had some average effect. And there was an average distance from that average effect. Now, with continuous ordered values, we run into an issue because we have much more information contained within these, which we want to actually apply to our models. And there is no obvious way of binning these data, meaning turning them into categories. And even those categories would still be ordered. So think back to the ordered logistic regression that we talked about with the trolley example. We had categorical data, but it was ordered, and we wanted to make use of that information. So the big takeaway here is that with ordered categories, or continuous categories to be precise here, similar values of these should have similar effects because they're grouped together along some continuous spectrum. So the question that arises is, how can we use pooling for continuous predictors? Because we always want to use pooling, right? Well, the answer to this is the misleadingly titled Gaussian process regression. Why is it misleading? Because it's not always using a Gaussian, but it's using a continuous process, which is not shackled to be a Gaussian one. It just has to be continuous. And so the example which we're running with here is the tool theory back from, I think it was chapter 11, which is where we talked about how many tools do we find on average on oceanic islands, given size of the population and a certain rate of forgetting about tools or just not using tools anymore. So we're interested in the number of tools in oceanic societies, and we want to account this time for spatial autocorrelation, which is the really neat continuous category, which tells us distance to other societies. So there may have been some exchange of tools between societies, but the further you're away from another society, the less of an effect there should be, because you're further away from them. So in theory, we want to add something to track how close the societies are. On the upper right-hand side, you can see our previous best estimate for the model, where we just had expected tools as a function of some intercept with some population rate, which tells you how much innovation there might be in a population given how big it is, and then just divide that by some rate of tools falling out of fashion and thus disappearing. Now we want to track the distance to other societies. So in this case, we can just add a factor for each society, but this has to be dependent on how far away we are from others. But let's first talk about how this factor would be interpreted, or how this parameter would be interpreted. And that comes from here. Because we have this exponentiated, a k value of 0 would mean that our society has exactly our expected number of tools given our previous best guess, our scientific model, as we called it back then, which I got hamstrung on because I thought that any model is scientific because stats is a science, but let's not get into that again. So when we have negative k values, we then have less tools than expected. And when we have positive k values, we have more tools than expected. Now, the big question is, what prior should we use here for k? And how do we make k for the society I dependent on location to other societies? And that's where we go into the Gaussian prior. Now, with the Gaussian prior, in this case, we have a multivariate Gaussian with all means being 0. We want to model the covariance matrix with pairwise distances. I know that's a lot. Let's talk about how we get here. So first of all, we have a vector of factors. The vector of factors is literally just the factor for each of our islands. So that's the k values, the interpretation of which I just walked you through, with 0 meaning as expected, negative and positive, yada, yada. Excuse me. This is drawn from a multivariate normal, where we just expect on average all of our k values to be 0. Why? Because k equals 0 means exactly as expected. No effect of distance to other societies. Now our covariance matrix, Kij, will now hold some effect of the pairwise distances to other societies. And this, I think, is quite ingenious. And I love how ingenious this is, even though it is quite complex. Maybe I also love it because it is complex and I love to torture myself. We'll never know.
There's one thing I dislike about it. Like, and I don't have a better solution. But it seems like the way I understand it is basically, if like Hawaii has like some other island close to it, right? Then because Hawaii is huge compared to the other islands, and they're correlated, then in some way, like it's almost like Hawaii will have less tools if there's another island close to it, because it's going to be correlated with it. I know that's not what I don't think that's how it actually pans out, because I think this is just like the extra stuff, right? It should be one, like it's a prior on the thing in EXP, which is like, which if it was one, it's stable. But it basically means that instead of having like an additive effect of having neighbors, it's more like you have like a negative effect by not having neighbors. And if you have the average number of neighbors, then you're back to 1. So it's a very counterintuitive way of thinking about it. Like, where if it was like a sum of like a more intuitive model would be like, so you have like all the tools from your own island, and then you have like some dampening effect on all the close islands, and that sums up to some number, right? Because like the intercept is totally messed up by this.
Yes, but what do you mean by dampening effect?
Obviously, if there's 2 islands and you just like merge them together, right? Then they will have more tools than they'll have more unique tools than the sum of 2 sub-islands, right? And therefore, like the closer they are, the more trait they are, and therefore they have more tools. That's the intuition. And like therefore, if it's basically like these, like the tools these guys have, plus like some extra stuff from this covariance matrix. That I think that's more intuitive. That it's basically like some number that is like an average 1, and then when there's a lot of neighbors, it's a number that is larger than 1, and then you stick that onto it. That's what I find confusing about this.
Okay, I'm afraid I don't see the confusion yet.
Like, let's just go through. Then when like maybe I could also just be wrong.
Fair enough. But let's soldier on for now. So in our covariance matrix, we want to understand the covariance of tool rates between island I and j in this case, where we have some maximum covariance, which is then modified by, in this case, the squared distance, as well as the rate of decline with distance. So the further you're away from from another society, the less covariance there should be between the number of tools that you have, because there's less exchange between you. And this is only covariance in number of tools through the effect of being close to each other. You might still have the same number of tools through other reasons, which is not driven through being close to each other. If you have multiple observations of yourself, there would also be a self-variance parameter in here, which our data doesn't have, so we don't talk about it for now. But it's just in this formula here.
Is there a reason it's squared?
The distance?
Rate of decline and squared distance? Is
Yeah, convention.
oh, okay.
It's literally just convention, because people used to do this so that negative values wouldn't fuck things up. And by convention, it's still being done.
It's also because variances are additive and sigmas are not, right?
Yes, you're right.
If you sum two variables, right, then the expected dispersion is the sum of the variance, not the sum of the sigma.
Yeah. Okay, that makes sense. Yep. I'm with you. Sorry.
No. Please do interrupt. Now we get to what does this look like? And this is just blatantly stolen from the slides. Just going to quickly show here. This is what a linear decline looks like. This is what a squared decline looks like. Fine, moving on. Just showing you that a linear decline has a much quicker decline than a squared one. So if you were to want to enforce a super steep decline, you just might want to take one of the squares out. Now we get to the model specification. And this time I'm not going to fly separate things in. You can just see how first we've got the Poisson model, then we have the lambda model that's dependent on our parameter k, then we have the prior for our k values with the covariance matrix k, which comes from that formula right there, which we've already explained, and then we just set the priors. Should make sense so far, I think. And this is where we get into how do we code this. So again, I went a bit wild on the highlighting here. But at least this time, all of the stuff on the left-hand side shows up on the right-hand side. So yay. Important thing here to point out is that to get to our Gaussian process prior, we now use a new prior, which is called cov_GPL2, which is the Gaussian process of L2 norm, whatever that means. It just works out to this formula right here. And I actually didn't mean to put that thing in. I just wanted to highlight the formula, and then I realized I'm in presenter mode, so I can't just click stuff and it will light up. On the right-hand side,
I think L2 norms means that it's the squared errors, right? So in like non-Bayesian statistics, you often regularize by either sigma or sigma squared. And if you regularize with sigma squared, then basically you're doing the classical thing of being a Bayesian, where you just pool everything a little bit in. And if you're doing sigma not squared, then you're doing lesser regression. Then you're pooling all the sucky variables in and leaving the rest extreme. And that's called L1 and L2 regularization. And therefore, like L2 regularization is the same as having a Bayesian prior. Like it's just a different way of writing the math.
Thank you. I didn't know that. Thank you very much. So again, right-hand side code, because we have a Poisson model, which has a log link, A, B, P, and G, as well as K, appear on the log scale. So if we were to look at the outputs, we would have to back transform them. Now, our betas and rows are strongly correlated in the prior. So you can see, right, God, where is it? Prior specification, where do I see the, yeah, sorry, here, DEXP 0.5. So we would argue that our betas and rows are strongly correlated from this prior. Now, in order to understand this, to make it a bit more clear, we want, of course, to plot the resulting distribution to understand it. But big thing to point out here is that if we want to have the actual underlying correlation matrix, which our model tries to understand, back at us, we could either do that GQ thing from earlier, or we can just take the beta SQ and the rho SQ and just parse that, and that rho should actually be RHO. I'll fix that actually right now before I forget later on. Sorry about that. You can tell I was running out of steam fast towards the end of this. Duplicate this and no, not duplicate. Sorry. What did I do? Okay, how do I get out of this now? Sorry, I did something weird there. I'll just quickly open the PowerPoint again. And slide, go back in, swap the presenter and view, and now I can do the sharing again. Glad you didn't have to see all of that. So in order to get back to the correlation matrix that we're interested in, so that is, sorry, just flipping back, this one right here, this covariance matrix comes with the correlation matrix, of course, and we want to understand the correlation between the different islands. And for that, we just parse beta SQ and rho SQ through the formula for K up here to then make the covariance matrix, which we get with K, into a correlation. That is a lot. And I realize that, so let's set that aside, because the code and everything is shown in the book and what have you. And I actually think we might get to a way of doing this in just a few slides, if I'm not mistaken. Let's talk about applications of Gaussian process models. This is frequently in use whenever we have continuous predictors which do have some relation between each other. So for example, with periodic functions, we might be interested in seasonality and we might want to model seasonality. We have spatial and temporal autocorrelation, spatial autocorrelation we just talked about. We might have phylogenetic distance, which would then lead us into a phylogenetic regression. Social networks can benefit from this if we don't have just multinomial nodes as we did in the previous example, but we have properly continuous node values. We could be interested in non-parametric splines and predictors. Again, Gaussian processes would be our helpers. Also, for something called automatic relevance determination, apparently this can help to estimate the importance of multiple distance matrices with the below formula, which was really just one short paragraph, which wasn't much longer than my summary here. So I'm just throwing it up. If someone runs into it and needs something like this, you've heard of it now. I've heard of it now. I don't know how it works. Let's just move on to the example of phylogenetic regression. I'm bringing this up here because I think this might be highly relevant to a few people in the audience. I know at least for Sam it might be. So here's me throwing it up. Basically, in this example, what we're interested in, and this is where, Serena, you'll notice that the model I'm presenting is switching around.
Sam has a small body, so now we need to figure out whether he has a small brain. That's where we are, right?
I think you will find, Sam, I don't even know how tall you are. You're probably a giant.
I don't know either.
No, me neither.
So, Serena, this is where you'll notice that I'm showing a different model than the one in the book, because right here we're trying to identify group size from brain size, I think. Oh no, sorry. We're trying to understand group size from brain size, and in the book I think they're trying to understand body size through brain size. But it's the same values, it's just a different DAG that we're interested in. So I'm just running with this one because I get all of the nice visualizations.
I'm guessing it's the same DAG, you're just making a different model because it's something else as the outcome variable.
No, you actually flip one of the arrows in the book.
Okay, that's weird.
Yeah, I think he thought the other one was more intuitive, and I agree with him. But at the point when I got to that model in the book, I had already prepared all of the slides, so I was unwilling to change.
Yeah, it's fine.
I did not update my prior on which model am I going to use.
No, it's because time is not a factor in Bayesian statistics, but it is in Bayesian decision making, right?
Yeah. So this is the DAG we're playing with, and we want to understand group size through brain size and body size. Now, we could express any linear model with a multivariate regression. We could also not. But for now, let's just consider our outcome here as just one single vector, which is just all group sizes explained through one mean group size and then some covariance matrix. And that covariance matrix factors into the variance overall with the identity matrix, and then mu I just being a product of an average group size, and then the effect of body size as, sorry, no, this is brain size as well as mass. So body size. The question that arises for us then is, or not the question, but all we need to do now is just add information to our covariance matrix, just to S. And this is where phylogenies come in. Let's again start off with a naive model, in which case we have this model right here, as we've seen before on the previous slide. But now on the right-hand side, we can see the model code, and IMAT in this case, which feeds into sigma, is literally just the identity matrix. In this model, we would argue that mass, so higher mass primates tend to come together in smaller groups, and bigger brain-sized primates come together in bigger groups. Again, there's a pretty good biological explanation for this, but we can definitely add some information to this, because surely we can do better by accounting for phylogenetic confounds. Because certain species will have evolved similarly, which might account for similar group sizes. So this is where we get into this continuous spectrum, because phylogenetic distance is continuous, and we want to understand how similar values in terms of phylogenetic distance lead us to similar values in the outcome group size. And this is where we can do an instrumental model, which we talked about previously. So in this case, we have some unmeasured thing, which is just our phylogeny. So now we have information about something unmeasured, which might just be a confound to brain size and group size, but also to body size. But let's not overcomplicate it for now. For now, we'll just say that brain size and group size are somehow confounded by phylogenetic distance. Now we could argue that covariance between brain size and group size declines with phylogenetic distance. It could do so linearly, it could do so non-linearly. In this case, on the right-hand side, we're going with a linear decline because we're doing a Brownian motion. And for the Brownian motion, all we have to do as a correlation matrix to be parsed into our sigma, which is our covariance matrix, we just have to parse in the inverse phylogenetic distance. Because inverse is literally just linear. Make sense? And suddenly, the effect of brain size disappears completely, and now it looks as though heavier individuals tend to coalesce in bigger groups, although not much. So this is where adding phylogenetic information leads us to a different interpretation of what's happening out there. And unfortunately, there's no definitive answer here to say this is the right model, this is the wrong model, because this question is still up for grabs in primatology of what drives group size.
So one thing I'm struggling with in my head is obviously body size and group size are also confounded by phylogeny, right? But like adding it in twice, that seems like the right thing. It seems like both of these two like predictor variables should be confounded, but I'm very unsure about how much of the body size confounded is basically captured in brain, since body size causes brain, and you have so like I can't really wrap my head around like the added value of having like a double confounded phylogeny.
Yeah, I also think that if we had the double confounding, we couldn't use it as an instrumental model anymore, because then it would influence outcome through yet another path or something. I'm not quite sure, to be honest.
I don't think so, right? Because it's both direct paths, right? Mm-hmm. So there's a correlation. Like maybe I'm talking loud now, so I like eventually I'll probably be wrong, but like there's one predictor variable which basically goes from brain size to group size, and that one has like this correlation thing because of phylogeny. And you could do the same with the body size to group size, right? So in let me see the code here, right? So you have in the matrix. Oh, crap. So where's I can't pass your where's the multi? I can't even figure out where. So there's this matrix magic, which is the stuff. Yeah, okay. I can't even answer my question because I'm so bad at reading these models.
All right. I actually think that PMBB. I actually think that the left-hand side DAG might not be fully corresponding to the right-hand side, if I'm reading this correctly.
Yeah.
Because the way I'm reading this, the way I'm reading the right-hand model, the phylogeny is actually impacting brain size and body size effects both on group
yes,
size.
I agree. I agree.
Actually,
like, because it's
actually doing what you and I
product of
wanted
these
it
two.
to.
Yes.
Yeah. Yeah, no, it's doing exactly what we both wanted it to do.
Yeah, yeah.
Cool. Just the DAG might need with might do with some updating. I did not make that DAG, by the way. I pulled that straight from the slides. It might also be that we're misunderstanding something in the model code on the right hand side.
Oh no, we're obviously right.
Right, that doy. So let's move on and talk about another instrumental model. So what if we want to account for a nonlinear covariance function? Well, luckily, we can estimate the covariance decline function. And for that, we can just throw up the right-hand side here. In this case, we are turning the distance matrix into a relative distance matrix. So the longest distance is expressed as
why do you call these instrumental models? In my world, instrumental is trying to find a confound that you don't like as a proxy for confound because of like this only one error trick. And here we're not trying to find a proxy. We have the confound. We're just like, it's just a weird number that we have to convert to a covariance matrix, right?
I call these instrumental because McElrich did.
Okay. Because
I would, yeah, no, I would not have called them instrumental by myself, to be quite honest.
Okay.
But maybe my understanding of instrumental models is just a bit too narrow.
Maybe it's just an instrumental model is when you have something that is an instrument, and instrumental variable is when you have a variable that's an instrument. And now since as we just talked about, it's basically like the whole outcome variable that has this covariance matrix, and therefore it's the outcome, and therefore the model that has the instrument. But I'm just like reverse engineering like the thing into concepts, so I'm like not very confident in my. Carry on. Sorry.
Will do. No, I love when you get carried away as well, because it shows that you guys are focused on this too. But let's finish this. This is the last slide I've got, and after that, I highly propose we do at least a 5-minute tea or coffee break, because I can feel my energy levels dropping quite a bit. Let's finish this. So basically, on the right-hand side, we try to get to an understanding of what the decline should be. And to do so, we just feed it a relative distance matrix instead of just a regular inverse one. And what we can try to estimate then with this CovGPL2 is the correct decline rate. So we can try to estimate the correct decline in that square bracket, sorry, in that bracket from earlier. That was the decline rate times the distance squared. Now, there are many possible covariance functions with multiple different things which we might want to account for here, which we're not doing. So for example, there might be variable decline rates on different branches of our phylogenetic tree. There might be different trees for different traits. So for example, body size and brain size might not be expressed through the same decline function given the same tree. They might be the covariance between these traits, so between values of these traits, might be different along the same tree. Do you see where we're headed with this? So there are no unique null models to go to covariances across our trees, and it's difficult to get to one covariance decline function for all of our traits in one go, and even for the entire tree at once. So basically, the note that we're leaving on today with this summary, which may be quite unsatisfying, is that we went through a lot of complicated stuff, and stuff isn't getting much easier. And this is where I'm just going to pause the recording and we just go into a coffee break. So recording started again. We've decided to not do any exercises today. It's going to be on the blog. Goodbye.